Okay, well, now I'm going to be discussing today the mass transfer aspect of pinch analysis and pinch technology. But first, I'd like to go over some of the cost evaluation methods that go along with some of the exchange networks and pinch analysis. And the main economic profitability criterion we're going to use to do this discussion today is the EAOC, or the equivalent annual operating cost. Now, the main term involved in this equation is the fixed capital investment, and fixed capital investment is one of those economic terms we learned back in chapters 7 and 8, which were methods to evaluate the manufacturing costs, just estimation parametric means to do that. Initially, though, the fixed capital investment is based on module costs, which are also another parametric cost estimations that are given in optimization. Basically, the equation for annual operating cost in pinch analysis is that multiplied by the interest, and then you add the sum of all the heating and cooling utility costs. For example, if you're doing a heat exchanger. To better cover that, I'm going to go over an example involving a heat exchanger and give the combined costs. Like Rebecca said, we're going to first and foremost you're going to have to perform your MUMMI or minimum utility minimum number of exchangers. And for instance, if you did your analysis just like Rebecca did, you came up with 8. In the text, they say the best way to cover everything is to use the total area and divide it by your number of exchangers, which you're going to give the area of one exchanger. And then from that area, that one exchanger, you're going to use the module cost estimate, which again is from parametric optimization, and use that as an estimate and for your exchanger module cost. Then say you have an interest of 10%, you're going to use a time frame of 5 years, and then round estimate is easy to get your utility costs, of course, which is water, cool water, and if you're using high pressure steam. And then your module cost states $97,000. That all plugged into the equation, all you get is $235,000 per year. Okay, now I'm going to start with the mass exchange part of the pinch technology. Basically, what you're doing here is to save mass, conserve mass, and so you don't waste raw materials. You get increased efficiency and economic viability that way, less pollution and less waste. The approach to this procedure is kind of the same thing, really analogous to what Becky covered, except there's a difference in physical phenomenon here. You have, as opposed to heat exchangers, the driving force is temperature. The driving force here is chemical potential, and of course there's several other thermodynamic relations that are going to affect that. But as opposed to heat exchangers, you're going to have a rich versus lean stream, and kind of the correlation there is if you're going to make the comparison towards heat exchangers, it's hot versus cold, because hot is transferring to the cold stream, and then say you're using utilities such as a scrubber or something, you're going to have the rich stream is transferring to the lean stream. And it's important to remember here that it's very solute-based streams only in this analysis. And again, of course, the procedure, like I said, minimum utilities, minimum number of exchangers algorithm, just as Rebecca went over. And then you're going to have, just like she did, the composition interval diagrams, as not temperature but composition. And you're going to have your cascade diagrams, and ultimately to come up with your minimum number of utilities. Okay, so to go over, there's some very key difference between heat exchanger pinch technology and mass transfer. First being the physical phenomenons. First and foremost is the partition coefficient. This one is basically the solute interface concentration ratio for the rich and lean phase correlation. In this equation, Y is the rich phase mole fraction, and X is a lean phase mole fraction, and M is that important partition coefficient that basically defines the stream. And then delta there is your minimum approach concentration, which is the one you're going to specify to be the minimum pinch point. Another thing, important parameter is the stream matching at the pinch. Above, you're going to have the flow rate, which is L, of the lean stream to be greater or equal to the partition coefficient multiplied by your rich stream. And below that's the opposite. Another restraint is your stream number of streams above and below. For above, you're going to have number of the rich streams less than or equal to the number of lean streams, and below it's going to be the number of rich streams greater than or equal to the number of lean streams. To cover this a little bit better in mass exchange networks, we're going to involve a synthesis problem. First, you have your process streams. Lay those out with, again, R is your rich stream mass flow rate. And of course, this one we have 3 streams. And given in the problem, we have our minimum approach composition of 0.01. And also is given is the physical parameter of the partition coefficient, which is 0.5. And then we have our composition interval diagram. Just like in heat exchangers, you're going to have your rich streams on the right side and your leading streams on the right side. And the totals at the very end, you're going to sum those, which is going to be your interval mass flow rates between those. Lastly, we have our cascade diagram coming down, the intervals in between, of course. And then a minimum number of mass exchangers is going to ultimately result with the 0.06 at the very left. What that means is a lean utility, and it says you're going to need another requirement of an additional separation unit, such as gas adsorber or something to take care of. And then synthesis, finally, after you go through your Mumney network, you have this resulting. And so in summary, the pinch technology optimizes synthesis of heat and mass integration in chemical processes. Talked about the exchange network and cost evaluation using our profitability criteria of EAOC. And again, the Mumney algorithm and procedure is basically utilized for both temperature and mass transfer applications. And that's it.